So here we were trying to write a code that models the stock market, right? So previously we had written two different functions, right? One was to okay, let me just open them. Split database. Oh, sorry, it's not related to this one. So this one is the stock market. One is the stock market price, and the third code was to plot it. Okay, so first one was to create the stock price. The stock prices were created by using a function that is modeled over here. Okay, so initial value of the stock into e to the power a function into time. The function is uh, the r minus zero point 0.5 sigma the whole square, right? So that function into time into sigma into w, where w is a process, random process, which defines the variations in the stock. Okay, so that was our first function, right, which takes these inputs and provides the stock value and the time as the output. Okay, that's inside the stock prices. The next code we wrote was to model the stock, wherein we try to take the inputs as how many stocks you want to create, what is the mean value, what is the sigma value, right? Standard deviation, the end value, and the starting value. Right? We pass those values, and we will collect uh, the details of the stock. That's what is in D. It contains the S naught value, initial value of the particular stock. This number of stocks can be 10, 15, 20, 100, etc. Right? As per the number of stocks we define, it will be created. Okay, so it's we are trying to write it in a structure format. So d dot s naught will be right that. So s naught will be of the specific size, right? Similarly, you have r and the sigma values of the stocks created in the same way. Also, we try to arrange. We try to create the names of the stocks because we are trying to simulate our own stocks, right? So we try to give names, right? A three-letter word will be created at random as the name. Okay, then okay, these two are over. Then in order to plot, we wrote a customized function that actually takes the values, the time, the s value, the stock value, and the symbol corresponds to the name of the stock, and it will print. Okay, so those are the three functions we wrote up here. And after that, now we are halfway through writing the main code. We are trying to implement the LSTM, right, for stock model prediction. So initially, you can see that we try to create the stocks, right, by defining the variables. Let's go step by step. So we can see that the first we should get a stocks. As you can see, right, the stock name is defined as the XQC, randomly defined, and it begins with a smaller value at the beginning, right? And if you remember, the N is the number of days, and T end defines the year wise, the number of years, right? So as you can see, since we defined the T end equal to 10, it's a 10-year stock market price that we are trying to simulate in this case. So you can see it begins from 0, 2, 4, 6, 8 up to 10. So 10th year, you can see that at the end, the stock reaches this value. Okay, at any point you can click and you can check, right? At the end of 4 years, what was the price of the stock, right? At the end of, say, 8 years, what's the stock, and so on. You can definitely move along and you can check. So it's completely random, right? Right? Randomly, it will generate. Now, if I try to run this itself once again, I'm expecting a different graph. Can you see? Right? It's a completely different graph. A lot of variation has been had in the picture in this. Right? So like that, you run this as many number of times as you want. You keep getting different. You see, there is this stock price is reduced. It was higher at the beginning, right? So it's not that we are trying to simulate only the ones which are going to increase. Now you also see there are stocks which are modeled and they are decreasing in nature. You see, right? Okay, right. So that's the this particular part of the stock, right? And then we wrote another function which in which we try to uh, gather the data and set it in such a format that you can directly use it in the neural network, deep neural network modeling. All right, so fine. So let's check what we did now. So here the variables are L is the length of S. From where you get S, S is here. Right? Okay, I'll just okay. So you can see here there is S here. It's a length that will be the S. In the sense, how many samples are there for each stock? That's what you are trying to uh, collect it into L, right? And the number of training data is equal to, as you remember, we had chosen 80-20% ratios for training and the testing of our data, correct? So 80% is indicated by zero point 0.8, right? Normally this L can be even a prime number or odd number, something like that. When you multiply by zero point 0.8, you may get a odd number or a fraction, correct? So for that reason, we are trying to bring it into the floor. Floor is the lower value, right? So just check. So when you use the function, built-in function called floor, what it's going to do, it's going to round the number towards the minus infinity, right? Towards the lower value. So uh, floor of say 1.8 is 1, right? So you see, it's towards negative infinity. In the sense, lower value will be selected. Even for negative, it's going to be the same way. You're not flooring towards zero. Floor means it is the smaller value. Okay. So if you have a value like minus 1.8, I am expecting answer as minus 2. Let's check. See, it's minus 2. So flooring always rounds your value towards the minus infinity, negative infinity, right? Always integers will be the result, right? And it is always minus. So you see that I'm trying to bring this to the lower integer. Whatever you get, lower integer, multiply L by zero point 0.8, whatever number you get. If it is a proper integer, keep it as it keeps as it is, no change. But whenever if this is not an integer, like a real number, it rounds up to the lower value. Okay, now you see the n train is the number of training samples, right? I'm out of my S, which is a stock, right? Stock data of 2531 values. 0.8% of those values will be assigned to the training data. You can, let's just check what will be the value. I have, so 2351. What I do, I'll multiply this with 0 0.8. So this is a number. I'll bring the floor of answer. So 1880. Okay, because this is 1880.8 in this answer because there is a E03 which is 10 to the power 3, right? So 1.8808 into 10 to the 3 is 1880.8. You see the zero point 0.8 will be removed and you keep only the integer value. That's 1880. Okay, so this is what we are expecting in the training data set. Sorry, among the whole data set, only the training part contains, S train is a variable, contains 1 starting from the first sample till the end train, which is 1880, right? Starting from 1880 till the last number, that is 2531, will be assigned to S test. Okay, then SVAL is equal to S train, right? Validation will be the training data itself because whatever you learned, you want to check that whether the learning is proper or not. Right. Then I want to normalize. So the process of normalization begins with calculation of the mean denoted by mu and the standard deviation denoted by sigma. Okay. S the mean is a function used to calculate the mean. STD is used to calculate the standard deviation of the matrix or the vector you present here or you pass as an input to that. Okay. So you can use a help. check this. So you can see that if you have a matrix, it's going to calculate the mean of that, right? Average or mean of the value will be calculated, right? Anyway, if you pass a multi-dimensional vector as input, right, it still calculates that, but you need to specify in what direction you want to calculate. All right. So, but anyway, right now we don't have to worry about that because our data uh, is a vector of one dimension. Correct? It's only one dimension, that is along x-axis. Right. Similarly, you can calculate the sigma. Right. So you just have to use a help called std for this. Just check. This calculates the standard deviation. Again, you have multiple options, like you can pass a multi-dimensional array, including the 3-dimension, 4-dimensional data, right? It will calculate, and the specific way in which you get the output depends upon uh, what's the dimension of the data and what dimension you specify. You can see here some examples, standard deviation of x comma 0 comma 1, 0 comma 2, etc. Right? So there are multiple ways of specifying the options uh, of calculating the standard deviation along which dimension you want. All right, again, right now it is one dimensional, so no need to worry. Now, so once you calculate the mu and the sigma values of your data set, right, the next objective is to perform the normalization. So I have two data with me, right? One is the training data and one is the testing data, correct? So for training data, this is the process. You see, S train normalized is equal to the data S train minus its mean divided by sigma. All right. Similarly, S test minus mu divided by sigma. Okay. So the value minus the mean divided by sigma will be the equation we are going to use to normalize the data set. Okay. I hope this is fine. So till here we had written in the previous class. Okay. Now what we do, we perform the required data set for the testing as well as the training, right? So we have S train, S test. Okay, everything is done. So S test normalized is also there with us. Okay, so let's start with S test is equal to what I do. I have actually index was testing data will be one lesser than the last data, because for the last data we don't have the answer with us. Okay, so what I do, I perform as, okay, first let me run this because I need to have all these variables with me. Let me run this part. Okay, so it's running till here, so without any error. Okay, clear the command window. Okay, now I'll, so what I'm trying to do here, s test is equal to the s test normalized starting from 1 till the last one, that is n minus. So one lesser than that, right? Now we'll go for the we'll begin with the training part of the neural network. Before that, I will create my uh, training data, testing data, as well as the validation data. We'll try to normalize. Okay, right. Uh, okay. I'll also do one more thing, because even for the validation data, I need the normalization, right? So let me do that here itself. Okay, that is S validation and normalize. Okay, I'll assign this to be the training part itself, that is S train normal. So you see already you have the normalizing data, right? So that itself you can just do. You can use it over there, right? So I actually, you see this is not needed. So the S validation is equal to S train. That part is not needed because I already have calculated the validation normalized. I assigned it here, right? So let me simply comment out that. Okay, so I don't need that. So I'll have comment. Right. Okay. So now let's start with the training data set. So X train is equal to, right? Training data, I'll put it one lesser than that. So you see, you use the current data set to predict your next data, correct? So that's why I'm using one lesser than this, right? So I can use only the till the last but one. So using the last but one, you should be able to predict what is going to happen at the last month, correct? Are you okay with that? Right? I can use my previous data to calculate today's data, right? In the sense, stock market, this is how it should work, right? This is our ultimate goal. I can see everything that is up to yesterday to decide what happens today, correct? Isn't it? So you see, I'm for a testing purpose also, I'm doing same thing. Starting from beginning, I go till the end minus one. So by using one, I create this, I should guess the second one. Using the second data, I should get the third data, and so on. Using the end minus one data, I should predict the end data, right? I cannot give end data itself as input because I don't know what is there after the end, because my data set is going to end at the index end, last index, correct? So that's why. That's the only reason, right? Why this is going. Okay, is it fine? So we'll do the exit train is equal to, I'll assign now. I have the train normalized, so that is S train normalized, in which you pick up starting from one till where? Till and uh, minus one. Are you okay? That is the X train. What should be the Y train? Can you tell me? Expected output of Y. Expected output of train. It's actually the S train normalized. For when I give one first data as input, what is the expected output? Just now we discussed, if you remember. When I give my first data as input, it should predict what? In the sense, first data in the sense, all the data till current, right? See, I want to predict today's price of stock, means I should use all the data till the previous one. So when I give, okay, when one becomes previous, what is your presence? Correct. See, my first stock price is the past data. So which is a present? That's what I'm asking. No, no, minus one is previous, right? I want the current one. So which is the current one? See, plus one, right? One plus one, that becomes two. So you see, I want to predict when one is given as input, the prediction should start from two, right? Right? Two, it starts till two. When end minus one is given as input, what is your prediction? Prediction should be the value present at end, right? Are you comfortable with this? You need, if you need explanation, let me know. Otherwise, if you're fine, I'll proceed. Okay, I'll tell you. Yes, sure, definitely. I'll explain. Now you see, I have a training data which is starting from one till end minus one. Okay, in the sense I cannot give end as my data, because if I give end as the data, it will predict the end plus one, which I don't have. Correct? So I am giving, let me assume I have 10 training data. I'm giving only from 1 to 9. So this is 1 to end minus 1, 10 minus 1, so 9. Okay. Now you see, when the first data is given as input, what I'm expecting, right? I'm expecting machine should learn that what is the tomorrow's price, that is second day price. So you see, when 1 is given, the output of my machine I'm expecting to be 2. In the sense, whatever data that is present at second position. Right. When the end minus 1, that is the ninth day, is given as training, machine should learn to predict the 10th day. That is end. So end minus 1 is given as input. The data present in end should be my output. This is what I'm expecting, right? That machine should learn because of the process. That's why it is in this way. Exit train equal to the data 1 to end minus 1. the Y train data should be starting from the second till the end, right? I hope this is clear, right? Okay, same thing will happen with the, okay, anyway, so validation is also same, right? X validation is equal to the X train itself because we assume the same thing, right? So again, you see, I think I can simply remove this. I don't want this because anyway, right now, depending upon the X train itself, I'm trying to do the validation, right? So you see, this validation normalized is not required. So I can directly remove. All right. So X validation is equal to X train. And same thing, Y validation is equal to, this is Y train. Okay, so it's done. So you see the size is going to remain same, right? X train, whatever is the size of X train, same thing will be the validation. Same data, whatever you give for training, you validate once again, checking that whether the machine has learned or not. Okay, all right. Now, uh, okay, now, fine. So let's specify. Okay, you see, I just ran this part and it's running fine. Now I'll move to the next. Okay, so in the next part of the code, let's try to do the specification of the network, right, which we want to train. So let's say, okay, let's try to take the how many inputs you are providing, right? The input size is, it's a one-dimensional array, right? So input dimensions, or I can even dimension it, it may confuse it at a later stage. So input size is equal to 1. Okay, only one input goes at a time. It varies with time, that's all. Okay, one input, in the sense one value will go into the machine for training purpose, right? So you see, this is a 1D array. It like a row, one row enters into the machine at a time, correct? So that's why input size is equal to 1. Okay, similarly, tell me how many outputs you expect. What's the output size of your this thing? It's a prediction of the price, right? It's a single variable. So I'm expecting one value at the output. Are you fine with this? Right. So let's define the number of hidden uh, units. So what you know that we can definitely start from say maybe 100 or something, maybe. Okay. Number of hidden units is equal to let me say 1. Let's try whether this works. If it is not going to work, later on we'll change. Okay, 100 or let's make it 200. This is the better suited one, I guess. Okay, fine. Okay, now, so let's define the layers now. Layers is equal to, you see, you are passing a time series data as the input. Okay, so when you give a time series data, in the sense the data which varies with the time as input, the input layer is called as, right, the sequence input layer. It's a sequence. Okay, so you can see that there is a sequence input layer. The sequence input layer. What should be the size? It should be equal to input size. Okay, let's give a name. Input layer. All right, so once it is done, the next layer it will be, let's say it's a LSTM. I give a LSTM layer as input, and this layer is going to have n number of hidden layers. If the number of hidden layers equal to number of hidden units, what you have defined. Okay, so number of hidden units. Okay, and now specify the name LSTM1 because it's the first LSTM. Is it okay? Then you see, I don't want to what you call write multiple many layers of LSTM. Let's keep it only one LSTM. Okay. So as you know, LSTM does not require any what you call activation function. Everything is inbuilt, right? You can go ahead with the fully connected. Fully connected, I think C is fully connected layer. Fully connected layer. And this layer provides output equal to the number of outputs. Okay, so outputs, what I wrote, output size, yeah, okay, output size. This is provide a name, and this name is fully connected one. Okay, so that's the fully connected layers, and we have given a name as well. And let's get an output. Final layer of this case is called as a regression layer. Okay, so regression layer, and give so you don't have to specify anything over there, just give a name. Okay, so name is the regression layer. Okay, I don't have to write anything else, so let's close this. I have to close here. Close. And here, and close this, and okay. So anyway, this defines the layers, and how do you check the layers? It's analyze. Analyze analyze network, and pass the layers to them. Okay, so let's check this part now, whether this provides the analysis of this particular layer. It's doing the analysis. Might take some time. Yes, but now it will come. Yeah, can you see? As per our requirement, it generated a network. Is it fine? So input layer LSTM1 fully connected and the regression layer. So you can see the details over here. It's input layer, sequence input. In the sense your stock data up till the current value will come as a sequence. That's why it's a sequence input. Okay. LSTM layer, 200 hidden units are defined, right? You can see the various parameters over here. Okay. Then fully connected layer on activation function. So 200 inputs will be coming. There is a one bias value for this, and there is a mean squared error used for the regression, because you have to regress to get your next value, correct? Use all the past values to guess your future value. So that's a regression. All right. Okay. So you can see that, right? This is the detailed network view of what deep neural network we have created. All right. So till here it's working fine. Let's proceed further. So let's go to the new category. So fine. So after this, now if you remember, the next option I should use is the specification of the options you want to train. Okay, so let's create options is equal to, the keyword is, it's a training option. Okay, training options. First is you need to specify which method you want to use. All right, so I'm going to use ADAM. Then you can specify various parameters. So the next one I want to define is the maximum number of epochs. If you don't specify, this keeps on training, right? You don't machine does not know when to stop. So uh, until and unless there is some convergence, it will not stop. So if there is no convergence in terms of generated error being uh, outside a smaller limit, right? Like maybe you define 0.5 as your error, but always the error is 0.65, right? Infinitely it keeps on running. Okay, so I don't want to do that. So I limit the maximum number of epochs to 300. Okay, so maybe first what do I do? I'll try to reduce this to 200. Let's see. Let's start with the smaller value, then we'll see. So the threshold value of the gradient with which the machine learns can also be specified. So that is the gradient threshold. You can specify this to be 1. Right. Start with the initial learning rate. Whatever you define, it will be used in the beginning. But later on, you can it will automatically make changes. So initial learning or learn rate. Initial learn rate is the keyword. You can start. Normally, we specify 0.01, but since this is a time series, what I have observed is that you can give much lesser. So start with 0.05. Okay. Again, this when you practice, you come to know, when you do various projects, you will come to know which type of project expects what type of learning. Okay, so again, it's you will there is no straightforward method to learn this, so it comes from practice. Okay, then so how do you want to update the learning rate, right? There is an option to use that, right? Previously we have not used it, but now I want to use it. That is learn rate schedule. So we have an option to use a piecewise linear model. Okay, so that is use a piecewise. So after that, so after how many iterations or how many learning intervals you want to change your learning rate, right? So it can also be right specified, right? So let's try to understand that. So learn rate, learn rate drop period. So after how many, after what period, in the sense after how many, what you call learnings you want to change, right? So 25. Yeah, keep it less. So 200 is given. So maybe I'll assign this to simply 75. Okay. Then by what factor you want to change that, that can also be defined. If you don't define, it will do whatever is the default value will be assigned. Otherwise, you can specify. Okay. So let's specify this now. Learn rate drop factor. So want to do this by a factor, say 0.2, right? Then yeah, we have used what you call the shuffle, right? I want to shuffle, right? So do you want to shuffle? So normally the answer should be yes, right? In the sense, the data should not go into the machine in the same pattern always. There should be, right? It should get shuffled. So how do you want to do the shuffling? What should be your option? It's every epoch, right? And specify what's your validation data. So specify in the form of what was the name given? Yeah, X validation and Y validation. Okay. X validation and Y validation. They are the validation data, and this is the expected validation output. Then, after how many iterations you want to uh, do the validation, that can also be specified. I think we have used this earlier. Validation frequency. Let's say every 10. You can reduce this if you want to check this further. Even 5 is fine. And whether you need a updation regarding how the training is being progressed and every epoch, how much is the efficiency, etc. If you want to see, the keyword is verbose, right? Do you remember? Right? I'll specify one saying that yes, and then I'll also ask to provide me a plot, and we'll say, right, what you want to visualize the training progress. So okay, so these are the options which I want to use. Let me check this. Yeah, training options are fine. So let's go for the training part. So net is equal to train train the network, right? So what are the parameters you want to pass? The inputs, correct? So x train. What's the expected output? That is y train, right? Pass the layers and also pass the training options. Correct? So use this and train. This is what I'm asking you. So let's try whether this runs. So it's, as you know, it's going to take some time, right? Because it's going to, normally it will use even the GPU we present, right? So GPU will be faster than the normal CPU. So you can see that training on a single GPU, right? You can see, right, the training table which is coming on the screen. Okay. Hello, can you hear? Am I audible now? Okay, now you can see here in this training process, the RMSE, the root mean square error and the loss have been plotted. You can see that initially they are larger values, and as the time progresses, this is the epoch, not epoch, iteration number 200, right? You can see it reduced to 0.07 from 1.02, right? Second one reduced, it was 0.18 reduced to 0.07. So see, the error and the losses are being reduced continuously. It means machine is learning, error is being reduced. Correct? Okay. So far it looks like the training is successful, right? But once we do the testing, we'll be uh, getting a clear picture of what exactly is being happening. All right. Okay. Now let's go to the testing part. So now I just need this net variable, which is present over here, right? If you can see, there is a net here. So if I open that net, it opens a network, which right has been changed. So you see the layers, number of layers equal to 4, right? So the sequential layer, sequential input layer, the LSTM layer, everything come, the complete details you can see, right? Which function has been activated, activation function, etc. Many things. Every detail you can see. The hidden states are there, right? So what are the values, right? Again, etc. This is after training. Once the training is complete, this is what, right, we get, right? You can explore about each and every parameter you have here. Okay. All right. That's that. So training is over. The variable net holds the complete details of the trained network. What are the optimum weights? What are the optimum biases, etc. All right. So let's try to do the prediction part now. So I'll call it as I say y predicted. It means it's predicted by the machine. All right. So this is the function is predict. I just want to predict what I want to use. I want to predict the input, some test data. I want to predict what is the next value dependent on by giving it to the network that has been trained. So predict using this network for the given data, that is S test. Let me just verify the name once. S test. Yeah, S test is there. Okay. S test is nothing but it's a test to normalize data starting from first data till end minus. Correct. Once again, this is valid. Whenever one is given, it I'm expecting the machine to learn predict the second data. Similarly, when you give the end -1 as input, I'm expecting that the machine should predict what? Machine should predict the end data, correct? The last data. That's why I'm giving one lesser than. Okay, fine. So this is what I'm doing. Now let us try to do some prediction. So we'll do the predicted output in two parts. Uh, Now you see what happened here is this predicted output will be uh, normalized data, right? But I don't want a normalized data to be plotted on the graph, because on the graph, whatever we collected here, right? So that is yes test, yes train, etc. Whatever we have here, there it is not normalized data, correct? See, we had something, we actually normalized and then we gave it to the machine. So what machine provides is something like the normalized data itself has the output, but I cannot plot it on the graph because graph had some other standard, right? So you see, this is what the graph has. Plot stocks of this. This is not a normalized data, right? Which means I need to convert my outputs given by the machine, right, to the other case, right? Other case in the sense I have to multiply by sigma, whatever you have here, multiply this by sigma, and minus mu becomes plus mu when it is moved to the other side, correct? So that's what I need to do now before I get the actual predicted data. So what I do, I y predicted of the first one to be assigning, right, the y, I can use a train itself, y train of one less than that, okay? Because you see the first data should be, the predicted data should be one lesser than the, right, and the y train the last but one data. That's what is going to be the predicted data. From there it continues because it is going to predict from the second data onwards, correct? So you see end -1, then the what should be the second data? It's the last data, end itself, correct? Y predicted of the second data should be the y train of n. First two data will be copied from the training itself, but after that whatever it predicted is fine for us, correct? Are you okay? Right, now you do the conversion of normalized data into the non-normalized data, correct? So I'll call this is, right, y, okay, now I'll call this as y predicted norm, all right, because it is actually in the normalized form. So y predicted norm is this. Now I am coming to y predicted. So y predicted is equal to, you should do the other procedure, like you have a sigma with you, right? What you do, you multiply with the y predicted norm. Okay, I had a minus mu over there, add it to this side, okay, plus mu. So this is the one which gives you the predicted output. Okay, let me try to run and check whether this is going to work fine. Yeah, so let me just check the predicted, y predicted. Okay, let me try to plot. Simply I'll call it plot. Okay, because anyway we are going to plot it at a later stage with the uh, actual data and the predicted data. We'll try to make a comparison later. So whatever plot we called earlier, right, that is plot of stocks, right, with this on this one, this particular graph I want to plot, right, this particular this thing, but for that I need to write some code. So as a so now I'll simply plot and show you what has been predicted, but later in the next session we'll try to plot this predicted data on the graph which we already have, so that we can compare whether the predicted graph matches the actual graph, right? That gives you an idea about, right, what machine has learned. Okay, all right. So plot of let me simply call y predict. All right, let me try to do this. And this is the output that we are getting as of now. So the predicted values are 506 in size. You can see right over here. It says that the size of the predicted data is 506 values. Correct. So similarly, you can see here, this is also 506. 506 data is 172 point something. Right. But right, we don't know whether this is correct or not. Anyway, so we have to write some more lines of code to automate the process of verifying whether this is correct or not. And again, we can bring the concept of accuracy out of the predicted values. How many are correct? How many are wrong, etc. We need to do that, right? So for that, we'll write the code in the next class.